and I'll let you do it.
So, good morning, everyone. So we're here with Dr. Juan Vivanco from the University Adolfo Ibáñez from Viña del Mar, Chile. He's gonna talk about collaborative projects related to mechanics of materials for research in bone tissue. Dr. Vivanco received a degree in civil engineering in Chile, and then he went on to do graduate studies at the University of Wisconsin, where he received, I cannot even name how many master's degrees in mechanical, civil engineering, whatnot, but eventually he specialized in bioengineering. And that's what he's a professor of, as I understand today, at the University Adolfo Ibáñez. Yes, it's a pleasure to have him here. And on a personal note, I have known him for many, many years. We have played soccer, in addition to being classmates in grad school. Yeah, so it's a great pleasure to have him here. And without further ado, I'll pass it on to Dr. Vivanco. Dr. Vivanco, please go ahead.
Okay, thank you, Fernando, for the introduction. Thank you, Tammy. Thank you, all guys are assisting in this talk. So my idea is to exchange experience coming from traditional engineering and with projects that I work with different people, with different institutions and different countries. So as Fernando was saying, I live in Chile, and which is sometimes difficult to collaborate with United States or Europe because of the distance and other limitations. But we have somehow we found a strategic to work together. So I think now, instead of seeing that as a limitation, it's a good opportunity. And since this is a graduate student seminar, I also want to share with you an option if you guys are looking for some other application or international experience in South America. Maybe we can talk another time. And that is basically the motivation of my talk for you guys. So, and in particular, I'm going to talk about how mechanics of materials approach for research in bone tissue engineering in collaborative projects. So I'm going to start with some, let me see, you hear me well? Okay. So, okay. So the way I prepare the talk is with a little bit of background and motivation, how I decide going to that area of work. And I'm going to talk later about 4 different areas of work, going from more basic science until more industrial oriented project. So yes, I went to my graduate studies in University of Wisconsin, Madison, and I was living there for more than 10 years. I have several friends. Fernando is one of those. Then I came back to Chile, where I joined to this university, Adolfo Ibáñez University, basically multidisciplinary technological projects in bioengineering, biomechanics, and additive manufacturing. When I was graduate student, I read some papers that kept my attention. As you were saying, as you are saying, there is one of in cancer cells. The editor of that journal was saying, "Can a biologist fix a radio?" He was explaining the importance of the multidisciplinary work and how the engineering is one of the good partners, not just to solve research questions, but also to develop tools to get to those questions. Plus the importance in to be involved in research, since undergraduate studies, all the value that you create to the society, that is also important. And at the end, something that I really like is, at the end, we work as a team. All the engineering work, all the science that we do is a teamwork. So all the research or result that I'm going to show is something that I work with several people. It's not my work. And understanding that give you a good point of view of how you approach those multidisciplinary team, multidisciplinary work, and such. Other things important as a background you guys coming from civil or mechanical engineering can understand sometimes traditional engineering when you use sand material. For instance, in the left picture, you can see electrical generator made of nickel and chrome material. Similar material can be used in other areas, for instance, in dental prostheses. The same in the windshield in that airplane that was used in the Second World War is a material made of polymer called PMMA, a long name, methyl methacrylato, PMMA. The same material has been used also as a bond cement for bone fracture as well. So what I want to say here, sometimes in traditional engineering, we develop some tools and materials that has been crossed to more biological application as those examples. And similarly, in the traditional classes that we have in mechanical or in civil or sometimes in mechanics of material classes, we understand the concept to study specimens in tensile, compressive, bending, with some standards, and we can determine some mechanical properties. The same idea, people study those properties, but in other applications. We can see in the right picture that is a scanning of a mice bone. We can see that it's totally different. The cross-section is not regularly changed, but with the same mechanical approach, the traditional engineering we can determine some properties as well. Other application that we face, special civil engineering in the asphalt materials, it's very common that we observe the rutting effect in summertime, and in winter we observe cracking in the highways, in the asphalt materials. So that behavior that happens is because that particular material, the asphalt, is a viscoelastic material. Similar behavior we observe in bone, natural bone. By the way, all the human body is made of polymer, so asphalt is a polymer. So the same concept that people study in the viscoelastic material as an asphalt, people study also in bone mechanics as a material. Okay, people in mechanical engineering will understand better that effect. That basically is a time-dependent property. And also in some areas in traditional engineering, there are some models, computational models based on finite element method that are very well established in those areas. Similarly approach people use to design implants with the same concept of stress, strain, constitutive relationship, all that finite element simulation, which is a virtual experiment, people using to design implants and other designs as well. And talking about the perspective of the material used nowadays, in general, generally speaking, we have polymers, we have ceramics, we have metals, composite. Plus, there is a new area of that is very well is appealing to design and to create things. The bioinspiration is how the nature gives us some ideas to design engineering applications. For instance, the healing materials, self-healing materials that are nowadays using to regenerate, for instance, crack that are in pavement, crack that can observe in roof. The concept behind is how the remodeling part of the fracture healing process happen in bone, for instance. So this is something that's given us an idea how we can understand better the nature, the biology, and we can transfer that knowledge to the engineering world and vice versa. So in general speaking, when we are in the engineering world, traditional engineering, we talk about engineering materials, man-made materials. And when we are in the biological materials, we copy those effects to the engineering material, we call the biomimetic materials. Both are in the concept of these bio-inspired biological materials as well. Showing the picture in the right, bone, some seashells, trees, those are very interesting material that full of capacity to understand, and plus are more sustainable in general. So one of the material that are very important in different areas, in aerospace engineering, in mechanical engineering, in as a smart material, because the way they can sense external stimulus is bone. Bone mechanics is a very well established area, and bone as a skeletal functions, it has mechanical properties plus metabolic properties. All the blood cells are forming in bone, plus bone is a big bank of calcium and phosphorus. The osteoporosis is a disease that happens because there is an unbalanced situation of those materials, those elements. And from the mechanics perspective, bone mechanics give us all the concept of mechanical protections, how the forces, all musculoskeletal movement and such. But for us, now is the idea to understand that bone provides mechanical and metabolic properties, plus as a material, it's a composite material. Sometimes people compare bone as a reinforced concrete. The concrete, the regular concrete, is the mineral part of bone. In this case, is a calcium hydroxyapatite material, and the steel part of the reinforced concrete is the collagen. But for us, it's a composite material, but basically those two phases. And bone as a traditional material can be studied as well with the same stress-strain relationship. And in that area, there are a lot of work happening to understand different parameters of those mechanical behaviors. For us, for the bioengineering application, one of the unique things of bone is a super efficient structure, porous structure. And when we say efficient, it's because it's very light, but at the same time, very stiff, and can provide unique properties that can be applied in different engineering applications as well. What I'm showing here is one of the earliest work where people in biology collaborate with people in civil engineering, actually. So we can see on the left side an image of how human femur, the trabecular are oriented, and in the right side, we're observing a crane, how the internal principal stress are distributed internally in that crane. And that was one of the first work that people in traditional engineering started work with people in biology to understand internal effect of the adaptation of these natural materials. And nowadays people follow different concept of the stress adaptation that the Wolff law was by the end of the 19th century saying the unique, efficient, and smart sensor of the bone itself. Also, bone is a hierarchical structure as other natural material, has unique properties because at different levels, going from the nano level, micro level, macro level, there are individual structure, and that also create a unique properties as well. And one of the main difference when we talk about artificial or man-made materials versus the biological materials is because biological materials are living materials, and particularly in bone there are some cells that provide that activity, and the interaction of cells, I'm not going to go to give details here, but in general there are cells that form mineral, other cell absorb minerals, and the other cell, the osteocytes, is the one that communicates the signal that's happening when you get the external force. For instance, when you go to the gym and you do a sport, or your muscle plus your bone get stimulus and develop more mineral. You can see in the X-ray of a typical X-ray of the arm of a tennis player, you can observe that the arm that the tennis player plays has more cross-sectional of mineral content. It's because that particular segment got more external stimulus. And that thing is within the frame of mechanotransduction in bone, how the external load finally is sensed by the osteocyte cells, the one in charge of the communication. And that is one of the main difference with the regular materials and the biological material. And if we extrapolate all the things in the public health, one of the main motivations, especially in the United States, is like around every year, around 30 million people suffer from musculoskeletal injuries. And I say the US because the US had good statistics and the public health sector is very well developed. In the countries from Mexico to the south, the public health system doesn't cover the diagnosis to evaluate those problems. So we are facing similar situation that in the States, they face in the 50s. So in the 50s, around the 50s, the United States created a special program for aging, a special program to attack better the musculoskeletal injuries. In Latin American countries, we don't have nothing like that. So all the statistics that I'm showing here is the number are established in the States, plus in the Europe, but we follow sometimes those statistics. But for us, the big numbers, you can see the health cost in osteoporosis in the United States was around 33 billion in 2004, and it's projected more than 42 billion by 2025. Okay, but this public health problem, the osteoporosis, is from the engineering perspective, we can observe this image, natural bone with a microscope, and the osteoporotic bone. And it's clearly that when you start losing bone mass, you can create a more unstable structure that eventually is mostly to get fracture, and because it's more brittle. And the technological motivation, there is a new area that was created in the States. It's called tissue engineering. It's a multidisciplinary area where people engineering, using the concept of engineering. As an engineer, we're very good in designing, manufacturing, and study complex structure. We are very good in science and math, right, and physics. And in biology, people understand very well all the process, cells, interaction with different cascade events. So the combination of cell biology with engineering, particularly biomaterials and biomechanics, has been an alternative for the traditional tissue repair to provide a good solution, but still we are not there yet. So there are needs to design organs, there are needs to design more materials to provide solutions that are not covering nowadays. And one of the key things that we study in South America is we think we have good science, we think we have good professionals and studies, but why we are not relevant in the international concert of research? So particularly in the orthopedic applications, only 1% of the high impact research are conducted in South America. And there are several studies that mention some limitation. I'm going to say just 3 of them. Maybe the English can be a barrier. We're changing that. So we think that as Latin American people, we are improving our communication with English mainly. So maybe that barrier is not limited anymore. And maybe there are limited access to funding. Yes, of course. Countries don't invest as much in other countries in funding, but we found a way to get some resources. But we think it's mainly because the disciplines of the medical doctors, they are more teaching and clinical care than research. But we need to find something that we call the champion. The way you find a champion, a doctor that want to do some research is one maybe one of the options. So this limitation give me another perspective. That's something I want to share with you. What do you think? Can mechanics of materials support research in tissue engineering? Can mechanics of materials or traditional engineering can support research in biomedical engineering? in order to develop physical and computational models of musculoskeletal system, in order to planning and evaluate orthopedic and rehabilitation procedures, with the idea of design better biomedical equipment instead of import from other countries. Can we do that? To planning better orthopedic surgeries and hopefully disease prevention strategic. So next, I want to share with you that some example of the traditional engineering, particularly mechanical and materials, can be applied in bone tissue engineering application, where concept of mechanics of material with some biomedical principles can solve with some perspective some biomechanical problems. And I'm going to start with this. This was a long-term project using a bioreactor concept. This bioreactor is this chamber here. In this chamber, we could put real bone and we can keep this real bone for almost a month living in a controlled environment. So this type of model are called ex vivo model. It's better than in vitro, but it's less than in vivo. It's a in vivo system out of the regular support of tissue, keeping in a controlled environment in a chamber that we can keep alive. And while we can keep alive with some culture medium, we can apply loading and do some mechanical testing to understand different variation of that tissue, natural tissue. So here, sorry, you guys think that it could be a little gross, but it's a not human femur that we can process, create some bone core, and with that bone core, we can create these cylinders that can be a microcomputer tomography image, and then we can put inside of that bioreactor and conduct that 1 month experiment and evaluate different conditions. Some cylinders are rested, other are dynamically stimulated every day, similarly as you guys go to the gym. And after a month, we observe one of the property called elastic modulus, that is basically the stiffness of the stiffness of the structure, increase after 3 weeks experiment after the loading condition. So with that model that was established in Wisconsin University, I was part of that study as well. We could show that ex vivo model can be an alternative to do a ex vivo experiment before going to in vivo or clinical application to isolate some factors in a controlled way. This is another work that we did with a cancer research institute. They were doing some genetic studies in mice to replicate what happened in humans. So they have 2 type of groups: natural mice, they call the wild type. The wild type in genetic, wild type is just the natural, and the other group of mice, they were with some genetic condition called the P10 block. So they want to evaluate if that particular genetic condition, how affect when you break your bone, and how is that healing process. So compare the control versus the one with the genetic disease or modification. So people from bone biology, from cancer research, they are very good and understanding those effects. So at the end, they fracture this femur of the mice, and they want to evaluate with engineering tools to know if the P10 block mice, since they created more bone tissue, if that amount of bone was only amount, also was a quality. So at the end of the study, we did some techniques that are very well established in engineering, with imaging, with mechanical testing, cross-section, and evaluating different things. At the end, we conclude that the main difference is just the amount of materials but is the quality the same type of material? So, and that was a important thing for people in genetic to understand and to continue doing some biological experiments to understand that effect. This is another big project as well that we conducted with people, with surgeons in spine, trying to analyze the implant. Well, this is a typical implant that you put in a column in the spine. Sometimes the implant is too rigid, it's too stiff, can deform the vertebra underneath. So they want to understand with engineering concept how we can solve those situations, maybe designing a structure with more porous, or maybe changing the materials and using the clinical approach as well. So at the end, what we did was we wanted to solve that problem, but we ended up developing some new methodologies in that area, basically coming from cadaver specimens, doing some clinical scan. With that scan, going to a typical segment process. You take the image, you clean the image, then with that segment process, sending the file to a CAD software application, and then with that CAD design, we can send into this virtual analysis for finite element applications. And one of the unique things here is that using the pixels that you get from the medical image, we can correlate somehow with regression, with Adolfo models, the density of the pixels, and we can assign, instead of using just one single material as an input for those modeling, we can assign more realistic mechanical properties of each pixels, creating a more heterogeneous structure for finite element analysis. All this process, people in different countries are using as well, but we created this to understand better how is the effect of vertebra when you design stiffer column implants. So here you can show you more results of that. This was a human from the cadaver vertebra, the process, all the imaging, and all the relationship with the density and elastic modulus that are important from the clinical perspective, plus all the mechanics happening there. Another project is in the joint replacement. So the first modern joint replacement was in 1938. So nowadays in the Western culture, it's very well established, the typical joint replacement. So before putting a joint replacement, what I say Western culture, from the United States all the way to Chile, the way the people use this is the surgeon, before putting the implant, they put a layer of bone cement, and the bone cement is a material that allows to be totally glue the implant with the natural tissue, and that bone cement is around 3 or 5 millimeters of the thickness. And one of the main problems is the infection. So what people do, usually they put some antibiotics, but the antibiotics is difficult to control when it's inside the body. So there are different alternatives that people are nowadays using for the infection. And one of those is the way that we are trying to create here is using nanoparticles. Nanoparticles with some antibacterial conditions that give that antibacterial properties without compromise the mechanical performance. So here we study different studies with different nanoparticles. One of those were the silica nanoparticles. Then we continue with silver nanoparticles, and then we're gonna continue with copper nanoparticles, but we didn't continue with the copper one. Coming from Chile, copper is one of the main things that we do research here. This is an in vitro. All this study was an in vitro conditions to creating bone cement with those particles. A lot of study from material science, chemical engineering, mechanical engineering as well, with different conditions. So at the end, with this, with the silica, with the nanosilica nanoparticles, we evaluate different evaluation as well of mechanical. And in the mechanical area, we study one of the effects called fatigue, when you have cycle of loading. And what we found that it's not needed that the increment of percent of nanoparticles increase the same way the fatigue properties. Actually, it was the opposite. Then with the same thing, we did some antibacterial studies, and at the end, we evaluate all the bacterial resistance, and those nanosilver particles are very well established. And nowadays, I don't want to show those results, but we're trying to use natural materials, create nanoparticles to provide as well these antibacterial properties as well. And then the third big area of work that we've been working is the use of scaffold structures. So generally speaking, scaffold are those temporary structure that in tissue engineering, this is a schematic way, people are using when you have a bone defect. Instead of the alternative using real implants, when you have a small fracture, instead of going to those traditional big implants, one alternative is use this degradable structure. It's called a scaffold that can be combined with cells, with stem cells sometimes, and that combination can be placed in the disease, in the defect area, and eventually all that structure can be integrated with the natural tissue, and the natural tissue recover all the functions. That is the paradigm. So what we're trying to do is, that is our approach in our lab. What we're trying to do is focus our study in that artificial structure that have material properties, structural and mechanical properties, some biological requirements, and study with two approach, from the mechanics perspective and with the biological perspective, which is the mechanotransduction. And that approach is using basically the biomechanical paradigm for this bone scaffold engineering. And we use cells as well, stem cells. Our approach is, some people say you can use the cell directly for the patient. We don't go to that path. What we do is we take natural tissue, and in the lab, we establish some protocols that we can recover the cells. I'm going to explain later what a particular example of that. And we can create all the cell culture in an in vitro condition. And we have established, this is our strategy to design this artificial structure, and we divide it in three main categories. One is design these areas and these structures. We can do simple design, we can do design with gradients, all the topology, all the math behind when you want to create those geometrical, more sophisticated structures. The second part is the fabrication. For the fabrication, we have developed also different methodologies to fabricate with bioprinting, changing materials, understand better all the additive manufacturing process during the printing process, all the thermal, all the rheology as well. And at the end, the assessment. And the assessment we had divided in two areas, from the engineering domain and from the cellular molecular domain. And we have a bunch of tools and equipment that we can study from those domains, and the integration of that give us that a platform that we can study those 3D structures with in vitro, with cell culture models in vitro for clinical applications. So talking about the additive manufacturing, we use FDM, which is the typical filament. So we use different filaments, we create our own filament with recycled materials, sometimes with biomaterials, plus the stereolithography system. Also, we use one of these SLA printer as well. And here I'm showing typical analysis that we do. We design, fabricate, some mechanical testing, find imaging, micro CT imaging to create those virtual models, combining with mechanical testing plus the simulations, changing some parameters. And sometimes we care a lot about the low cost equipment, low cost material, but with a smart way to trying to replicate and have very defined internal structures. We use also, this is a collaboration with some people in Switzerland. We have access to this expensive equipment called bioplotter. In the bioplotter, we combine bioglass with polymers, clinical based polymers, and a lot of parameters that can be controlled to finally get structure like this one. Here we have a scaffold with different porosity and with different materials. These are for clinical application, is particularly with PCL, is a special polymer, FDA approved, with some bioglass, and that bioglass particles are particles that are bioactive that promote bone integration. And all the engineering concept behind that we can understand is taking imaging from microscopy, taking imaging from micro CT to understand the accuracy of the process, to conduct some mechanical testing, to understand how some important parameters can change, plus the internal factor in the rheology process. Since it's a thermal process during the printing process, there are several factors like viscosity, G prime, G double prime. People that are familiar with those factors can understand better, but it's basically the rheology when you study something that is in a liquid shape during the manufacturing process. That is very well established in our lab. And we create our own printers. We develop some sensors that we can improve the thermal conditions. We can melt higher temperatures some plastics and polymers. We have others biological printers as well, like the incredible one here for hydrogels, and we interact that with stem cells. We have a special protocol to develop some stem cells that I want to show you. This is another application scaffold, but instead of polymer, is made of ceramic. We did a bunch of experiments with different scales, nanomechanics, micromechanics, and macromechanics for the mechanical part, plus all the cell analysis. Here are some results. What is nanomechanics? Basically with a indenter, with very tiny indenter, and you want to determine some properties of your specimen at the nanoscale with some protocols that are very well established in special electronic materials. We can determine those properties as well. And going more for clinical application, we develop a special procedures. So the gingival tissue is the tissue that when you go to the dentist take out a tooth, and that tissue is going to the garbage. Instead of going to the garbage, we take that tissue and we develop a special protocol that other people have used around the world. So in that case, we collaborate with people from Europe. In the lab, that gingival tissue, we can get the stem cells, adult stem cells, and with that cells, we can continue doing different studies with biology to evaluate cell proliferation, cell addition, cell differentiation, going to the bone cells as well. And we have also very well established using this cheap way of getting tissue for those cell applications. That's basically the main areas that I want to share with you guys. And I want to say special thanks to this group. B3MAT is a research group with more than 20 people, faculties, students, graduate students, people from other countries as well. It's called Biological, Bio-Inspired, and Biomaterials. And we're trying to find different way to give value of natural materials to provide some solution that sometimes are super difficult to find, especially in Latin American countries. We are located in Viña del Mar City, which is a twin city of Valparaiso. Both are considered the college cities in the country. And you can see all these red colors are universities in the city. So but that is the main reason. It's a college town, and there is a nice environment to do local collaboration to get access to different equipment and resources. We are located here, where is the star. All the others are institutions that we collaborate regionally, plus our collaboration, international collaboration. This is the view of our campus. Now, the picture that you see in my background is a picture of that building facing to the ocean, but I'm not located there now. Now at home. So with that, I'm gonna say that just I want to give that idea of bone tissue engineering application with bone mechanics, with bone biology, but also we do research with marine biomaterials. We are studying how the global warming affect the ocean Pacific, and we do a bunch of studies on those materials. This is an image of micro-CT imaging. We conduct some mechanical testing on that. Plus, since the seashell, the seashell of, let's say, oyster seashells are made of calcium carbonate, and the human bone is made of calcium phosphate, those are cousins as a materials. We are using those natural marine materials as an alternative for bone application. We're putting cells, and cells love it, that material. They stay and they grow, and we're trying to develop a new approach to provide, in a cheaper way, bioactive material for bone regeneration based on marine resources. And with that, I'm going to mention the same question at the beginning. You as a PhD students think maybe can mechanics of materials support research in tissue engineering and biomedical engineering using those concepts? That is the main message for you. Thank you. I'm open for any questions now or later. You have my email. We can communicate if you guys are interested. But now I'm more than open to receive some questions. Thank you very much.
Thank you so much, Dr. Vivanco, for a very interesting and informative seminar. Yeah, now let us open it up for questions. Feel free to ask questions either on the chat that Tammy will read, or else just speak up. So please,
we do
questions for Dr. Vivanco.
Yep, we do have a first question on board. It says, hello, Dr. Vivanco. My question is related to bioprosthesis. Can these biomaterials be applied to design bioprosthetics? The materials used in these days are for non-invasive, but can a material be designed to approach invasive to define a limb with sensors to make a human part for a disabled person?
Yes, that is really good question. That is super multidisciplinary work. Some people are going to study very well the robotic part, all the movement. If you are very interested in that part, there is a open software developed in Stanford. It's called OpenSim, that create all the important part of the movement. That is movement biomechanics. Here, what I'm showing is more like the mechanics in biomechanics. So combine that knowledge, combine the sensor that is very well established in other disciplines. People are actually develop these new limbs applications, and the biomaterials, there are studies in biomaterials, there are FDA approved biomaterials, and you of course can combine biomaterials with sensor include with this other perspective with the movement, and that is cutting edge research. People are doing that.
Thank you.
I have a question, Juan, or Dr. Vivanco, sorry. So yeah, you're focusing on the mechanics of the materials, whatnot, but then there is also all this aspect of sensors and data collection, data analysis, cyber physical systems, all of that aspect, right? That you can like collect information from the body potentially, and then make decisions, analyze the data and make decisions based on that, right? So to what extent have you collaborated on that regard? Because I mean, I asked that question because that's where in a way electrical engineers come into play. So that's what I'm asking that particular question.
Really, really good question. So I'm going to explain you maybe one example of project that we're doing. For us, let's use this image. The image, the CT image, is a bunch of data. Just picture with pixels. For us, is numbers, and we when we collaborate with people from the statistics, for instance, or from computer science, for them is data and colors. What we provide is the physics behind. Instead of just doing regression, maybe without any knowledge, we say, let's use this particular law. And nowadays, what we're doing is with some people in Rush University in Chicago, we are collaborating with computer science in a way to get a more optimal process. Instead of analyzing what image that's time consuming, we can program it, but not me. People in the computer or electrical or in data science, they can create some algorithm to analyze faster and more automatic way those imaging, and we cross that information with the orthopedic disease. And that is one of our future projects that we want to collaborate. And of course, we're more than welcome to do things because we don't have that knowledge. We understand the physics, the mechanics behind, but with some replicate, let's say 20 replicates, we don't have the skills to analyze thousands of data. Very good.
Any other questions for Dr. Vivanco?
I guess I had a question. So my question was, have the bone scaffoldings been implemented into actual patients? And if so, do they adapt well to the existing bone? Kind of like, do they have a similar strength profile?
Yes, this good question. That particular scaffold, the one that I'm showing here, is just only research, an in vitro condition. The last example they show, the bioceramic one, those are made of materials that are nowadays used in clinical application as a material. So anytime that you go to the dentist and you have they have to fill something you have in your tooth, they use calcium and phosphate materials. Medical grade, of course, medical grade that's more expensive. So, but the structure, the 3D structure, some people are using, I don't know if massive they used, but in let's say, I remember in Georgia Tech, people were using with some bone application, but preclinical studies. But since those materials, the calcium and phosphorus materials, are very well established, it's not the material itself, it's how we can create a structure that reduce the healing process. So the research, I didn't mention in detail here, yes, I want to give an overview, but the research, let's say that things is currently used and available, but the research is going now. If you have a fracture, are you well prepared to go to the gym immediately? Are you well prepared to do some marathon, or are you ready only to walk? So dealing with that time, the healing process is now the future questions that people are trying to discover.
Thank you.
Hi, Professor. I have a question.
Hmm?
One of my research topic is about promote the bonding strength between soft material to like chemically disciplined materials, like a soft material to hard material. For example, silicon rubber to like acrylic, like normal plastic. The approach I was doing is like to design some microstructure or like a macro structure on the surface of the hard material, and then to provide some mechanical locking to lock the soft material. The application we were thinking about is purely in like consumer electronics or some other like industrial kind of application. But from biomechanical point of view, what the application can you think of for this kind of research? Thank you.
Yes, good question. Yes, that is one of the new areas of research that people are doing. Anytime that you have a connection of two materials, let's say tendon with bone, there is a mismatch of properties. That area in a tissue engineering is called interaction tissue engineering. So anytime, for instance, cartilage and bone, if you want to provide a solution for a knee application, since you have two levels of tissue, You will have a soft tissue plus a hard tissue. That integration is not very well analyzed, and people are doing that analysis. Plus, the new thing is going, how about gradients? Since you are doing with hybrid structure, hybrid materials, something that you can also use is the gradient. The nature provides gradients in everything, gradients, physical gradient, chemical gradients. So the and in the mathematical area, there are good equations that you can design geometry that are not easy to identify. So you can use the gradients to change microarchitectures, plus you change the material itself. And in biology, in any time you have a connection of tendons, ligament, or bone, or wherever connection of tissue, since are coming from different origins, that is very important, deal with soft plus hard tissue. Here I explained only hard tissue application, but in the interface, I think that is the weakness part, all the interface. Thank you.
Thank you very much.
Any other questions from the students? Well, if not, Juan, I guess to wrap up, I would like you maybe to share your experience, how is it that, was it for you to walk from, civil engineering, which is really your background, into bioengineering, right? So what would be your advice, say, from for someone that is studying mechanical engineering or perhaps civil engineering and is considering to move into bioengineering? Did our lack of knowledge in biology, was that a problem for you?
No.
So that's kind of like, if
good questions.
Like a general advice on that regard.
Yes, good question. I have the chance to work in an orthopedic company in the United States. And when they will hire people to do these implants or those advanced projects, they prefer people with the background in fundamental engineering, electrical engineering, mechanical engineering, and such. Because still biomedical could be as a fundamental, it's not very clear what is the fundamental. So having your fundamentals give you the opportunity to work in whatever other things. And then the collaboration. So I'm not expert in cells, I understand the cells, but I work with my colleagues from biochemistry or biology. But for me, something that changed totally was this type of seminars. So when I was in graduate school, having the chance to have people in seminars with different backgrounds, you start connecting, as the question that the students are asking, you start connecting, I can apply this for the other type of applications. And when you are in a nice environment of education, as you are in the university, when you are in your PhD studies, I think that is a wonderful time because you are open to absorb knowledge. When you talk to somebody in totally different area, when you're drinking a beer, observing this, observing the different perspective. That was the thing. When I was in Wisconsin, I was in a traditional area, and that was my experience. Other people have done with the same. And keep your eye open when you observe. And we've been the whole process of our life observing phenomena in engines, for instance. But sometimes when you start observing the nature, you get inspired with that thing as well. So all these bio applications has been progressed a lot because the engineer, as an engineer, the way of our thinking, we have some way of analyze that is more than welcome in other areas. So we're very structured and we're very objective oriented. We're very objective oriented. So I would say having your fundamentals clear, then you're going to start applying other things.
Perfect. Yeah, thank you so much. I appreciate your answer. And maybe another question there, Tammy, would you like to read it?
Yep. Logan says, in your field specifically, what educational backgrounds are in most demand? Example, MD, PhD versus Metatronics Masters, currently completing undergraduate in electrical engineering.
I think as more demands, all of them are more demands depending on the perspective and how deep you want to go. for me, one of the areas that I think are articulating is electrical, electronic, and mechanical engineering. You can put those areas in the center and they can collaborate. Let's say as electrical, computer science, you can deal with medical images, you can understand signals. And as a mechanical engineer, you can design process, you can design processes, and well, so for me, coming from civil was more difficult, but I did a transition in mechanical engineering, and I have a lot of colleagues in electrical engineering. So with those two areas, articulate with others, I think. And nowadays, all this is if I have the chance, I would do with data science. It's not just observing data, is the way you can use the data and the way you report the data to others. So all the tools now, I think, is in whatever application, but you have to do your task. It's not something easy. You have to study. It's high demand. Everything. Yes, everything has obstacles. Good thing when you do a PhD, whatever major as a PhD, you already are prepared to solve those obstacles. You develop somehow that skill that you have something that can be difficult. Somehow you will solve it and you will come with a solution. It's like our training. So I think you guys at the end of the program will be prepared without fear. It's just you can observe, approach, you can find information, and go ahead.
Thank you.
Okay, so any final questions or comments for Dr. Vivanco? Well, if not, thank you so much, Juan. It's been a pleasure see your face and listen to your voice and listen to the work that you're doing. And yeah, we'll be in touch. So thank you so much, and have a very good rest of your day.